So, welcome back student to the next class of nonlinear optics and its application. So, today we will going to it is lecture number 55 and we will going to study the stimulated Raman scattering. In last class we have already started stimulated Raman scattering. So, let us go back to the topic once again. In spontaneous process, what happened that the molecule is excited by some external photon having an energy h cross omega p, and then go back to some final and then have some final state, vibrate some, go to some external some higher energy state, and as a result we are getting some kind of photon which is excited from the medium having a frequency less than that of the launched frequency. So, this is the Stokes process. In stimulated Raman scattering process, we want to amplify these waves omega s. In order to do that, we launch not only one omega p photon, but also h cross omega s, which is the energy of the Stokes wave, and in the output what happened, this omega s is amplified. So, if I now try to understand these things in terms of mathematical treatment, then omega p omega s is launched. Omega p and omega s corresponds to the field frequency are the two frequencies corresponds to the field E p and E s, which is the pump field and Stokes field. In the plane wave form, I can write the pump and Stokes in this particular form, which we already used. Total field is omega p and omega s, E omega p plus E omega s, this is the total field. Microscopic polarizability should be there, it is epsilon 0 microscopic susceptibility multiplied by total electric field. The form is exactly same the way we represent a polarization. P is epsilon 0 chi 1 E. If I compare these two form, it is the same form. Instead of this, I am using a new term alpha, which is microscopic susceptibility, because we are dealing with one molecule, but the total polarization can also be figured out by multiplying, this is some sort of approximation, by multiplying in the total number of dipoles or molecules here per unit volume, and still this susceptibility microscopic susceptibility term is still there, which is a function of q. So, in last class we try to find out the differential equation of the molecule that is vibrating, because the form of q is important and we were try to find out what is the form of q. And once we know what is the form of q, then only we can find out what is the nonlinear polarization. P nonlinear is important thing, that is our aim, and we know that P nonlinear, which is it is in epsilon 0 d alpha dq evaluated at 0 multiplied by q and E, we have derived that. So, this q, the information of this q is needed, and how do I find this q? For the molecule that is vibrating because of the electric field. So, I know I need to solve this differential equation, which is a forced damped oscillation equation. So, force term I calculated last day. So, today we will going to solve this equation. Well, in order to solve this equation, I write the q in these two form, half q 0 e to the power I omega t plus q 0 star e to the power minus of I delta omega t. So, q and q 0 are complex amplitude which has a frequency delta omega, because we know that the molecule is vibrating with a frequency omega. That is why this differential equation, the generalized coordinate should have a frequency component delta omega, but the amplitude may not be real, it is a complex amplitude. So, in general I can write q is equal to half of q 0 e to the power I delta omega t plus complex conjugate of the total term whatever is used. Also the E square information is important, because here you can see in the right hand side we have E square term which is a force term. So, E square is the total field, because E is E total field is E of omega p plus E of omega s. When I make a square of that and write the explicit form of E of omega p and E of omega s, we will get this term. Since we are making square, this half term will be 1 by 4 E p to the power I k p z minus omega t as usual, E s e to the power I k z minus omega t plus complex conjugate and square of this. Now, I write k as k p minus k s and omega as omega p minus omega s to reduce some or to make the expression compact. E square, please note that E square is having many frequency components. When you make the square term, then you will have one frequency omega p with a multiplication of 2. So, 2 omega p one frequency will be there, 2 omega s another frequency will be there. So, this 2 omega p 2 omega s is some sort of second harmonic generation kind of stuff. But apart from that, there are few frequency components, and one important frequency component that we have is omega p minus omega s. This omega p minus omega s term is important because E square is a force term. If I go back to this equation, q is vibrating with a frequency delta omega. So, in the right hand side I need, this is a force term. So, that has to be one component delta omega. So, E square having a component delta omega basically force the molecule to vibrate with a frequency delta omega. So, we need to find out what should be the frequency component omega of the term E square. Exactly the thing we are doing here. When you calculate E square, then we derive or take out only those terms here which is vibrating as a frequency delta omega. The component of E square with delta omega frequency is this one. So, how we will get this frequency delta omega? So, omega p minus omega s, it is simple. So, omega p minus omega s means this has to be omega p and omega s is negative. So, that means we should have a star of this quantity, which is complex conjugate is here. So, which we will have. So, that means E p multiplied by E s star should have a frequency component delta omega like this, and also the complex conjugate of this term should be there, and if I make the complex conjugate of this, we will have a delta omega term again here, but with a negative sign. You can see a negative sign is sitting here. So, I will have a plus delta omega term. This is nothing but the complex conjugate of whatever the term we have here. So, E p E s star is the amplitude, 2 E p E s star is the amplitude, that is important. Also note that the phase term should contain K p minus K s. So, K p minus K s, I reduce this K p minus K s term to K. So, K z minus delta omega t, this is the frequency, the term corresponds to frequency delta omega. So, E square may have different frequencies, only we are taking those terms which are the frequency component delta omega, because this is the source term for the molecule that will going to vibrate at the frequency delta omega. Well, after having everything in our hand, we will put that to the equation. When you put that to the equation, we will get this kind of expression. So, we had the equation in our hand, which is q double dot. Let me write this equation here. Q double dot, here double dot means the derivative with respect to time, double derivative with respect to time, then plus gamma q dot plus omega r square q is equal to the total force term. This total force term was epsilon 0 divided by 2 m, so far I remember, del alpha del q at 0 and E square. So, E square we know it should be the component of delta omega, and here E also the component of delta omega. So, when I put the value of q and E having the component delta omega and put it here in this differential equation, I will readily have this expression in our hand. We readily have these expressions, and when I put these expressions, then we need to solve, because we have here the delta omega thing. I write this entire stuff as L function of delta omega to reduce or to make the calculation more compact. So, L of delta omega is omega r minus delta omega square plus I of gamma delta omega. So, L of delta omega is a complex quantity, please mind it, and if I put it here, then q0 is a solution of this equation, because we have already a form of solution. I already have a form of solution which is q0 e to the power of I delta omega t plus complex conjugate. So, this was the solution, and in order to have explicit form of the solution, we need to find out what is my q0, and exactly this is the thing we are doing right now. Put this solution here and extract the value of q0. So, when we extract the value of q0, it is now simply epsilon 0 2 m L of delta omega del alpha del q0 E p star E s e to the power of minus I k z. When I write q0, mind it, when I write q, one thing I should note here. So, q is written here, the frequency component of plus, the frequency component is plus delta omega t. Here the frequency component is minus delta omega t, but this is plus delta omega t. So, if I want to find out q0, then I need to write this frequency component both the side. When I write this frequency component both the side, this term will appear 2 E p star E s. If I look very carefully in this equation, here we have this term E p star E s, because we are using that form e to the power I delta k delta omega t. So, q0 I will figure out. Once we find out q0, then it is easy to find out what is q0 star, because q0 star is nothing but the complex conjugate of the previous term. So, q0 is this. So, q0 star is epsilon 0 2 m L star delta omega del alpha del q0, and complex conjugate of this is E p E a star, which is just the star is reversed and e to the power I k z. So, q and q0 we evaluated, that is important. So, once we have the q and q0 term in our hand, then we can write this q0 in form of amplitude and phase. Q0A here is the amplitude. So, here we find the total value. So, what we do here to make it more compact, I write Q0 bracket A, which is the amplitude part of that. So, the amplitude part contain from here to here with the phase e to the power of say minus I k z. So, the complex amplitude Q0A is now in this particular form. Why it is complex? Because EP, ES may be complex, and here L sitting here, which is also complex. So, we can write the total Q0 as epsilon 0 this EP star ES, and here in amplitude, here in amplitude and phase form. So, once we have Q0 in our hand, the next thing is to find out the nonlinear polarization in Raman process. That is the ultimate goal, because nonlinear polarization is something that we need to figure out. So, let us quickly recap what was our nonlinear polarization. So, P was n epsilon 0 q of alpha, alpha of q and E. Alpha of q is expanded as alpha 0 plus d alpha dq multiplied by q, because this is a weak function of generalized coordinate q, and after that we divide these things into two parts, P linear and P nonlinear. We called it P linear and P nonlinear. The nonlinear part contain this q term, and P nonlinear is defined in this way, where q and E are multiplied. Next, we need to find out what is my q and E. Here we write q, this was our solution, and this was our value E. So, q we solve the forced oscillation using the forced damped oscillation model for a molecule. We calculate its generalized coordinate q, and when we calculate the generalized coordinate, it comes in this particular form. So, when it comes in this particular form, you can see that we have EP and ES, these two fields sitting here. When this q has EP and ES term sitting here, and then it will going to multiply it with E. E is also having one EP and ES. So, when you multiply this q to E, so overall weightage of E will be E cube. This is very important thing that you need to understand here, that why this Raman process is included in chi3 under chi3 process. The Raman process is included under chi3 process because chi3, in case of chi3, P nonlinear is equal to epsilon 0 chi3 E cube. Here also the P nonlinear term is of the order of E cube. That is why it is some sort of chi3 process. Well, Q0 is in our hand, Q is in this particular form, E is this particular form. So, the next thing is to calculate P nonlinear, which is very important, and now we will going to calculate P nonlinear because everything is now in our hand. So, P nonlinear is the multiplication of Q and these things E with this term. So, Q is sitting here, EP is two terms, E omega and E omega p and E omega s. So, now I write the extended form of Q, which is half Q0 delta omega t, Q0 star delta omega t with a negative sign, with I, EP Kp z minus omega t Es e to the power I Kz minus omega t plus complex conjugate. So, I write the total form of Q, I write total form of E, and then I am going to multiply that. Before multiplying, you should note that how many different frequency component P nonlinear should have. Here we have delta omega, and when it is multiplied with EP, we have omega p. Again it will be multiplied with omega s. So, we will have some sort of term delta omega plus minus of omega p, this frequency will be there, delta omega plus minus of omega s, this frequency will be there, delta omega with a negative sign plus minus of omega p, this frequency is also there, and minus delta omega plus minus of omega s, this frequency is there. So many frequency components can be possible here, because P nonlinear will contain this amount of frequencies, which is obvious that when you multiply Q with E, then this amount of different frequency will come up. So, when we multiplied omega p with this, we will have delta omega minus omega p, which is one of these frequencies. When you multiply this quantity with this, then we will have minus of delta omega minus of omega p, one of the frequency components sitting here. In the similar way, we have the complex conjugate term is there. So, you will have all these frequencies in your hands. Well, we know that P nonlinear is now having different frequencies. So, if I now start writing all these frequency components, so we will have these amount of frequencies as we mentioned. So, again go back to the equation of P nonlinear, because P nonlinear now we are going to calculate, or we are already in the process of calculation, and when P nonlinear, we use the value of P nonlinear, it is epsilon 0 n del alpha del q, half of q 0 this quantity, and EP this and this. So, different frequency component, as I mentioned in the previous slide, should be here, and if I write all these components, so P nonlinear should have this frequency component, this frequency component, this frequency component, this frequency component. So, total 8, there is 2 frequency component, here we have also 2 frequency component, here also we have 2 and 2, total 8 different frequency component it should have. But which frequency component is the most important one, that is something we should be careful about, because P nonlinear, when we try to find out what is the evolution of the stimulated cases, the Raman stimulated process, what happened, that I am launching electric field with frequency component omega p, I am launching another electric field with frequency component omega s. Molecules are here, due to the interaction it is now vibrating with a frequency delta omega. So, delta omega is equal to omega p minus omega s. Now, this wave will come out, and when it is coming out, omega s, which we call the Stokes wave, is amplified. So, evolution of E s and evolution of E p we need to find out. When omega s is amplified, that means amplitude of this omega s field, which is E s, will going to amplify. So, if E s is going to amplify, we need to find out what is the differential equation of E s. In order to find out the differential equation, we need to know what is the source term of that, which is P nonlinear. P nonlinear is the source term, and we find here that the P nonlinear is containing this much of frequencies. So, in these frequencies, if you look very carefully, there is one frequency which is omega s, and this is omega p minus delta omega. Among these frequencies, delta omega is omega p minus omega s. So, omega s is omega p minus delta omega. When we have omega p minus delta omega, you can see this frequency is sitting somewhere here, omega p minus delta omega. So, p NL omega p minus delta omega is sitting here, omega p minus delta omega. So, I can write that this term will contain one frequency omega s. Also, here it should be omega p, there is a printing mistake. Also, omega p frequency is also here somewhere. Omega p is omega s plus delta omega. So, omega s plus delta omega is sitting here. So, one nonlinear polarization among these 8 frequencies, one nonlinear polarization is also vibrating with a source frequency which is omega p. So, we have all the different frequency components in our hand in p nonlinear term. So, we will only take those frequencies which we will going to generate inside the system. So, in our case Stokes frequency we will try to find out what is the p nonlinear for Stokes frequencies, as well as the pump, the frequency for the pump is omega p. So, the nonlinear polarization term for omega p is also important, that we will going to extract from this expression. And in the next class we will construct the differential equation for the Stokes wave and the pump wave, and try to find out how this Stokes wave going to amplify in this process. So, with this note, let me conclude this class here. So, thank you for your attention and see you in the next class, where we will going to discuss a very important process called Raman amplification and try to understand how the signal is amplified under Raman amplification. So, thank you and see you in the next class.